Good day, everyone. I'm going to speak to you about polymers. This one should wrap up pretty quickly. Okay, so just a brief overview. We're going to go over the types of polymers and conventions in terms of how they're written out. In terms of repeating units, because polymers are going to be very long and vast in terms of repeating units. So we're just going to show what a monomer is going to form, just sort of generically. Then we're going to go over the mechanisms. So free radical mechanisms, something you're already familiar with, anionic and cationic. So in other words, you're going to see sort of for anionic, sort of a nucleophilic addition versus cationic, where you're going to see more of an electrophilic addition. And then condensation, so in other words, nucleophilic addition, elimination. And then it's a little bit of cross-linking, but I'm not really going to get too far into that. So we're really going to look more at linear constructs. Then we're just going to quickly go over some applications and then finally some analysis that's involved with polymeric structures. So polymers are really kind of a major sort of subclass of organic chemistry. So you're not going to get too far in depth with what we're going to cover today. Not as though you haven't had enough to cover already, or we haven't had enough to cover already. So the first type of polymer we're going to discuss today is polyethylene. So it's sort of your generic, typical plastic. So linear is going to be very much sort of in a straight line fashion. So that means, if you're thinking about intermolecular interactions, if you have quite a few chains of these and they kind of stack neatly, sort of like lawn chairs would, it's going to be a very high dense material. Okay, so it's going to be a lot more robust than something that's going to be branched. So this is going to be low density and this is going to be high density. So HDPE, so high density polyethylene. Again, things that can stack together versus branched. You can see a diagram there in your text. So low density polyethylene is where things are going to branch out and be a little bit more malleable and all over the place. Okay, so another example of a polymer that's rather simple is polypropylene. So in this instance, notice how you don't see anything hanging off of either of these two carbons that are part of this long sort of hydrocarbon chain. With polypropylene, you're going to see a methyl group hanging off of there. Okay, so what previously exists is most of these monomers are all going to be vinyl. Okay, or have a vinyl beginning, at least ones that have free radical or cationic or anionic mechanism involvement. So, in other words, you're going to see repeating units like this. Again, N just, depending on whatever the degree of polymerization is, that's going to dictate how many repeating units you have. Okay, so what's hanging off of this main chain here is what is going to be referred to as a pendant, sort of like if you had a necklace with no, gem or anything hanging off of it, you wouldn't have a pendant, right? So nothing to sort of make it special, if you will. Now, polystyrene is going to be a larger pendant. So you might have seen styrene previously. So we'll just shorthand this and just put pH here. So again, this is just going to be a phenyl ring that's going to hang off of this linear chain that has been previously formed by, let's say, some kind of chain reaction where you have pH just repeating. Now, your text kind of gives an example. Remember the two carbons that are going to be repeating here are coming from the alkene. Okay, so the vinyl alkene is going to be most reactive. Really the best way to get this repeating head to tail, which is going to be most favorable and most stable. So if you have two phenyl groups that are right attached to one another, there's going to be a lot of steric bulk interaction. It's going to kind of distort them and make them a little funkier. The best way to do this is through cationic mechanism, which we'll get into in a minute, instead of free radical. Okay, another that you're going to see is PVC or polyvinyl chloride. So that's just going to be some kind of repeating unit of chloro group, okay, hanging off. Now, PVC is something you're going to see in piping, right? So in other words, if you're going to use some kind of base to unclog a pipe or something like that, it's going to be a little bit more protected than, let's say, using an old lead pipe or something like that to get your drain or whatever unclogged. Okay, so in other words, it's a pretty stable compound, but over time, if this is exposed to, say, something like light, this will break down and form HCl as a byproduct and kind of degrade. So PVC is actually, I used to work in the additives industry for PVC, so you would have antioxidant compounds that are kind of mixed into the matrix here to make sure that things wouldn't break down over time. So PVC, if you're thinking about piping, there's other applications for PVC. So if you think of siding, if you think of windows, stuff like that, fenestration as well. So in other words, fences, that's all, when you see that sort of vinyl fencing, that's all made of PVC. So if those materials are meant to withstand, let's say, things like high UV, reflect off, you're going to have less of a breakdown of this type of polymer. Now, just to note that this is going to be a halide pendant that's going to be hanging off of here. So something else that's sort of chemically inert is PTFE or Teflon. So these are saturated with fluorines. So Teflon is going to have a repeating unit that looks like this. Okay, so in other words, you're going to have these electronegative atoms that are really going to be reinforcing this repeating unit. And you see right here. And, there's really nothing that can break this down. You can have this under very high basic concentration and really not see a change or breakdown in terms of using Teflon types of plastic. Okay. Now Kevlar, so I said suiting up with amides. So this is really, this is an amide that's formed between a repeating unit with, like a phenyl ring, for instance. So it's going to be very robust, a very elaborate pi system. Let me see if I can get a repeating unit here. Okay, so that repeating unit is going to be a little bit more elaborate. Sorry, I don't have that dedicated to memory. But, kind of fighting a fever or something here. It's not feeling too good. Nonetheless, have this repeating unit you see right here. Okay, so in other words, really the repeating unit that you would see is, notice how there's two N groups and then there's two, what do you call that? Two carbonyl groups that are wedged on that are para to one another about one ring. So in other words, it's not like this typical repeating pattern that you see here. It's one and then the other, one and then the other, one and then the other, one and then the other. Okay, so this is going to form via condensation reactions. Okay, so some mechanisms of formation here. The free radical mechanism, so it's likely to form the more stable radical during propagation. So you have some initiating source that's going to interact with that alkene and kind of break the pi bond up. So you're going to have that radical form in the most stable position right there. Okay, so this is going to be secondary as opposed to just primary on the other side. So then you're going to form, your next sigma bond with the next monomer. Okay, and then that's just going to repeat. And again, the head to tail, in other words, it's going to go pendant, least substituted carbon, pendant, least substituted carbon. The head is always going to be the pendant. Least substituted carbon is going to be the tail. Okay. All right, and now on to cationic mechanisms. So an alkene is behaving as a nucleophile. So just like you saw in chapter 11 from last semester. So you have a hydrogen source, which again is going to be behaving as an acid. This is going to pick that hydrogen up as a base, sort of. Then you're going to have a positive charge over here at this carbon. Again, this is going to be the most stable carbocation that you would form. So that's going to really make sure that you have a most stable carbocation at each step. So it's almost the same here with this previous example with free radical mechanisms. But remember that free radicals, once those radicals form, it's really sort of a heads or tails, no pun intended, in terms of where those two bonds can form. There's no, if you remember back in chapter 25, there's really no energy barrier between the bond formations of the two. So where the two singlets match up and meet together, there's really no bond preference, if you will. Okay. Now, so this will just repeat on and on and on, and then you always have that sort of leading carbocation where the next monomer is going to attack and amend to it. Okay. So then, or the alkene rather, of the monomer. Okay, so the next is going to be anionic mechanism. So it's going to be a lone pair kind of pushed forward, right? So this is going to go to the next alkene. And again, this is almost like a conjugated addition, if you will. So it's going to be a nucleophile, a nucleophilic addition. So again, it's a nucleophilic addition, not a substitution. Okay, so it's just going to kind of form a chain reaction over and over and over again with one lone pair going to the next to every other carbon, and so on and so forth. Okay, so the ring opening polymerization is going to be going from a cyclic ether to sort of linear polyethers, right? So you would start off with calcium oxide, which is going to be a really aggressive base. Also act as a good nuke, so it's going to pop that ring right open depending on how many carbons are part of that ring. So it's going to be a saturated ring, of course. So you need to have some carbon that's slightly activated. The more ring strain that is, the better off you are going to have with reactivity. So you're going to see, maybe a 2, 3, 4 membered ring, or 2 or 3, 4 carbon count of a linear structure, and then attack one of those sides attacking the next But remember that even if this is negatively charged twice, this is, several nuclei removed from the next negative charge, so it's still going to be stable. And you're also going to have, let's say, calcium here to stabilize everything, calcium 2 plus, right? Okay, then condensation polymerization. So this is the last type of mechanism we're going to discuss. I'm not really going to go over any examples. I just want you to be able to kind of pick apart what you may see on the final in terms of, oh, this would be a condensation polymerization versus this would be free radical. So there are plenty of examples that you can work out in your text. I'll be sure to send you a couple of practice problems if you want to work on that on your own. But I'm not going to go over any particular examples here. I'm just going to try to give you the bare bones because, again, you have a lot to worry about. So not exclusive to water as a byproduct. Okay, so HCl can form methanol in other cases. So in other words, this is going to be a nucleophilic addition elimination reaction. So if you want to have a little brush up on that, you can look at chapters 20 and 21. Okay, so you're going to have your weak nucleophile that's going to attack this electrophile here. You're going to have some kind of leaving group about this C double bond O carbonyl. Okay, so whether that be an ester or whether that be even carboxylic acid or a acid chloride, you're going to have some kind of leaving group going off with a protic hydrogen as a byproduct. So again, HCl, methanol, water, those are all quote-unquote condensation products. Okay. Now, so this Q just means that it could be a nitrogen, it could be an oxygen. So I'm just writing something sort of generically that's going to amend to that carbonyl ultimately and form, whether it be an amide or an ester. Okay, so it can either form an ester or an amide as polyester or polyamide. Okay, so two examples, one of which we already discussed was Kevlar. Another is going to be nylon, so it's going to be some kind of polyester. Okay, so it's just some general uses and applications. Of course, medical, right now with the pandemic, you can think of polypropylene is going to be used to create a N95 mask, right? So it's going to be proper PPE that you would need that some of us just don't have. And then filtration. So if you use acrylonitrile and you make a polymer out of that, you can use that for filtering water. Okay. And then building materials. So there are plenty of types of building materials, anything from composite decking, again, to PVC, PVC piping, for instance, for plumbing. Law enforcement, again, Kevlar is going to be a very bulletproof or bullet-resistant polymer that's going to, save you from a bullet wound. Food packaging, so you can think of cellophane. So cellophane is more of a natural product. So it's coming from cellulose. And then it has, maybe some kind of rayon or something there doped in with it to give it some kind of elasticity or what have you. Excuse me. Then shipping. So shipping, you're going to have, let's say, something like, styrofoam, right? So again, styrofoam is another form of some kind of packaging that could be used. So whether it's something that you're trying to ship is fragile, right? So you see some of those peanuts. Some of those are getting replaced with cellulose today just because it's more biodegradable. And then insulation as well. So, polystyrene is a very good insulator. If you're at a truck stop or at a gas station or something, sometimes if you're in a pinch and you need a cooler to cool some drinks, whether you're going out into the woods or just hanging out by a campfire or something like that, it's not a bad thing to take along. Okay, so these are all different types of uses and applications for some of the polymers I've already discussed with you. Lastly, we're going to look at analysis. So to actually measure the degree of polymerization, to actually try to separate out, polyethylene glycol or different types of polymers that you would put together by any of the mechanisms I previously described. You could use something like size exclusion chromatography, which is essentially a type of stationary phase that has sort of these pockets, if you will, and then these globs that come down. Right, they're not all going to separate out. You can't just sift them out. So they're going to be rather macroscopic and small in size. So what they'll do is they'll actually fit in within these sort of cavities of these beads, and depending on how large or how small these monomers are, they'll stick into those beads and have different retentions relative physically to how they're going to be flowing through a particular system. So there's also particle size analyzers that you can find. So lasers or sort of optics can delineate different sizes and get different populations of polymers and how great or how small they are in terms of size or repeating units. Lastly, what a lot of polymer engineers use for looking at thermal transitions is differential scanning calorimetry. Now remember earlier in the discussion I was telling you about how there are different types of additives that go into particular types of polymers. So, when you see PVC, whenever you see any types of plastics, never is there a plastic that's made through an extruder or some other mean injection molding, whatever have you, that is, just the polymer itself. The monomers, they get cooked together and then boom, you have a product. That's not how it works. There's always something else that's in there. It's almost like trying to say that, oh, I'm going to take these monomers, I'm going to cook them all up together, and I'm going to get, a perfectly good plastic that has, no susceptibility to breaking down or anything like that. There's always some kind of additive for different types of applications, different types of strain, whatever have you. You can almost think of it like baking a cake. You're not just going to take flour, throw it into a pan, add some water, and expect a cake to come out, right? You're going to have other things in there. You're going to have binding agents, you're going to have eggs, you're going to have whatever else that's going to go into the sugar. You're going to have a whole bunch of things that go in there to actually make it taste good. Otherwise, if you just throw flour and water in there, you throw it in there for 45 minutes, you cook it, you're going to probably have a fire or a big mess in your oven or what have you. So that's really the breakdown of everything. So differential scanning calorimetry. Calorimetry, remember, is going to be sort of an energy drop or absorption or what have you in terms of what kind of breakdown you would have. So for instance, calorimetry, like you learned from Chem 1, is going to be a breakdown if you just added oxygen to X number of moles or X number of grams of something like let's say carbohydrates or some kind of fuel that breaks down. So you want a standardized energy difference. So differential scanning calorimetry is going to be looking at a mixture. It's not going to be looking at one sole analyte or component. So when you're looking at these thermal transitions, you're looking at what is referred to as a glass transition. So a glass transition is simply when something isn't completely molten. It's not, this glorified melting point apparatus. I used to think that when I first got into industry, but when I've got acquainted with some of the technology, this is really different. The differential scanning calorimetry has a sweep not only of the change in energy, which is on the y-axis, but the temperature sweep, which is going to be on the x-axis. So you can go back and forth in terms of, heating and then cooling. And you can see that based on when you heat curve as opposed to when you're cooling, you're going to see different temperatures in which you're going to see drops or adding of heat energy. Okay, so just for your own edification, if you want to check it out, I think it's kind of interesting. But if you're more into medicine and that kind of thing, then it's probably not much of interest to you. But nonetheless, I told you this one is going to be short and sweet. Hope you enjoy it. And the last one that's going to be coming up here in the next day or so is going to be mass spec. Have a good one.